So before the midterm, we discussed these some technique to solve convex optimization problems, right? Although it was more general in the sense that you could potentially use it for non-convex optimization problems as well. It turns out to be the most useful for convex optimization problems. We saw that solving a constrained convex optimization problem is essentially the same as solving for a set of conditions called the KKT conditions. If you're able to solve a set of equations, then you get the solution to your constrained problem. Right. But in order to do that, we have to be able to identify whether our problem is convex or not. And in the problem formulation itself, we have to try to formulate it in a way so that we end up with a convex optimization problem. And of course, we also need to see why the KKT conditions work. Right? It was an algorithmic technique, but when does it work? Why does it work? How do we end up with this dual optimization problem and the KKT conditions? Right? All of those things are yet to be seen. So we were discussing some conditions or tests for convexity of a given function. Right? So the standard definition of convexity is just the following, that you want, so the convex function could potentially be defined over any convex set, not necessarily over all of Rn, but we saw that if a function is convex over a certain convex domain, then you can always look at the extension wherein outside the domain you just define it to be plus infinity. Then you end up with a convex function which is so you end up with a function which is convex everywhere. Okay, so we'll go back and forth a little bit in the classes. In general, I'll assume that the function is convex everywhere, but we may end up with functions which are convex only in certain domains, and you want to perform optimization in that particular domain. Okay, so this is the definition of convexity. But in many cases, it is either not helpful. Suppose you want to test whether a given function is convex. It's not always easy to check for this particular condition. And the geometric interpretation for this particular condition is that given any 2 points on the function, or basically given any 2 points on the curve for the function, the straight line joining these 2 points is always lies above the curve. But on the other hand, we also had this first order characterization, which was if f is differentiable at all points in its domain, then the function is convex if and only if the tangent at any point on the curve always lies below the curve. Okay, so these are two equivalent geometric characterizations of convex functions. So we saw a proof of this, and a third characterization was the second order characterization. We saw that for real numbers, so for functions over the reals, a function is convex if and only if the second derivative is always non-negative. So the generalization of this to functions over Rn is that the Hessian should be positive semi-definite. Okay, so we'll see a bunch of examples of functions which are convex, which are not convex, and see which of these tests are helpful in identifying whether a given function is convex or not. For functions over the reals, typically you can look at the second order characterization, the second order test. You find the second derivative. If it is greater than or equal to 0, then you can conclude that it is convex. But for more complicated functions, these tests are sometimes not sufficient. There are other tricks that you can employ. In particular, we'll see how do you generate new convex functions from simpler convex functions. And that is sometimes even more helpful in identifying whether a given function is convex or not. So let's see a bunch of different examples, some of them very simple. Question? Yeah.
This is necessary and sufficient.
This is necessary and sufficient, assuming that the Hessian exists. Yeah. So all these three conditions are necessary and sufficient. The first order condition is also necessary and sufficient, assuming that the first derivative, that is the gradient, exists at all points. Correct. Yes. First or the second derivative. Or we will see some other ways of generating convex functions. So if you can use some of those properties. So one simple condition that we saw in an earlier class was that if you have a function, if you have let's say n different convex functions over R or Rn, then the sum of those functions is also going to be convex. In fact, any non-negative linear combination of those functions will also end up being a convex function. So if you can express your maybe complicated looking function as a sum of simple convex functions, then you're done. That function is going to be convex. Okay. So let's see some examples. So let's just start with f of x equals e to the power, let's say, alpha times x. What does the curve look like? So is this function going to be convex or not convex? Yeah, it's convex for all alpha. Okay, and how do we prove this? Okay, let's just find the second derivative. What is the second derivative of f? So second derivative for any point x is going to be equal to alpha square e to the power alpha x. Right? E to the power alpha x is always greater than or equal to 0, and for every alpha, alpha square is greater than or equal to 0. So this quantity is greater than or equal to 0 for all x and for all alpha. Okay, so that's simple case. What about x to the power alpha? Yeah, root x is not convex. Well, it could be. Is it convex, concave, anything? And is it convex in a certain region? Yeah. When alpha is even, it is convex. What about mod alpha? So what's the test that you would use? Again, let's compute the second derivative. So what is the second derivative? Alpha x is equal to alpha into alpha minus 1 x to the power alpha minus 2. Right? So when is this greater than or equal to 0? For what values of alpha, for what values of x? Yeah. Alpha greater than 1. What if alpha equal to 1? For alpha equal to 1, what is x power alpha? It's x, right? It's a straight line. So is it convex? Yes, it is convex. It's both convex and concave, right? So that's a simple case, but when is this greater than or equal to 0? So suppose alpha is greater than or equal to 1, then is it greater than or equal to 0 for all x? No, right? For what values of x is it great? Is it guaranteed to be greater than or equal to 0? X non-negative, right? Oh, sorry, it depends on alpha. You have to be a little careful. So x in general greater than or equal to 0, this second derivative is going to be greater than or equal to 0. So for alpha greater than or equal to 1, if x to the power alpha is convex in the region 0 to infinity. Okay. What about, so suppose I have alpha greater than or equal to 1, then f of x is convex over what happens when let's just stick to alpha greater than or equal to 1. What happens for when alpha x is less than 0? it is not defined for certain alpha. What about x? Okay. So just be careful whether x is between. So sorry, why is it not defined for certain values of alpha? Alpha can be 3 by 2. Okay. Okay, fine. So let's take the case when alpha is greater than or equal to 2. Yeah. Okay. X raised to 0.5.
Effectively, alpha minus 2 should not be able to express alpha minus 2 as some positive constant a by 2 raised to k.
Sure. But in that regime, what do you think f of x would look like? So let's just take x cubed. Let's just take some. Let's take alpha to the power 2.5. Say, okay. What does the function look like? So, or maybe let me take an integer value of alpha. So x equal to 3. Okay, so what do you think happens for x less than 0? Concave, right? What if I take 4? Evaluate. Is it convex? Okay, so let's go back to this particular quantity. So for what values of alpha, let's, so no matter what alpha is, as long as it is greater than or equal to 1, f of x is convex for x greater than 0. Okay, so we're interested in what is going to happen when x is less than 0. Okay. Yeah. So for what values of alpha, I should say, suppose x is over x less than 0. For what values of alpha is f going to be convex, and for what values of alpha is f going to be concave? Yeah. So alpha even, again this is alpha even and alpha greater than 0, right? F is convex. If alpha is odd, then f is concave. Right? Okay, so how do you define f of x for which one? Correct. If alpha is just greater than 0, then this quantity would be negative, right? Exactly. That's why I wanted to consider that separately, right? So if alpha is even and alpha is greater than 0, I'm sorry, so I should say alpha greater than, yeah, so it's at least 2, right? Yeah, will be 2, correct. So that's fine. Correct, correct. But if not, so let's say that alpha is less than 0 and alpha is even. So let's say alpha is less than or equal to 0. Right now, no, so this holds whether alpha is an integer or not. When alpha is greater than 0, so in this case, I'm assuming that alpha is an integer, right? In both these cases. So when alpha is less than or equal to 0, what happens? Sure. For let's alpha less than or equal to 0 and x defined in the interval 0 to infinity. Yeah, it's always convex. Because alpha into alpha minus 1 is going to be, so alpha is negative, alpha minus 1 is also negative, so x to the power alpha minus 2 is that's anyway going to be non-negative. For odd values of alpha, so what? Sure. Okay. But x is greater than 0, right? Correct. So now if we assume again integer values of alpha, correct? So alpha integer, then for x in minus infinity to 0, what can you say about f? So again, alpha into alpha minus 1 is always going to be positive, right? Because both alpha and alpha minus 1 are negative. Yeah, so it's concave for what alpha? Any alpha? Again, odd versus even, right? So if alpha is odd, then f is concave. And f is convex for alpha even. Why? It depends on alpha, right? So let's consider alpha to be minus 2. Okay, so f of x is equal to 1 by x square. What would the second derivative be equal to? 6 by x to the power 4. Now for x less than 0, is this non-negative or is it negative or positive? It's always positive, right? So it's convex. But on the other hand, if I had, let's say, 1 by x, then the second derivative would be equal to correct 2 divided by x cube, which is negative for x less than 0. That would be concave. So I just want to see a plot. Equal to, let's say, minus 3. Maybe I should have just plotted for 6. It's concave for x less than 0. For x greater than 0, it's going to be convex. So it's going to look like this. Okay. Okay, what about log x? Because this is defined for x greater than 0. Okay. Again, second derivative test. The first derivative is 1 by x, second derivative is minus 1 by x squared. This is always less, so strictly less than 0 for x greater than 0. Right? So this is concave. Yeah. If f, yeah, for some x, okay. Again, this is for one particular point, right? So you can't say anything about convexity or concavity of a function at one point. It's over a set. So you're saying f of x equal to f double dash of x is equal to 0 for all x in some set? Then it's both convex and concave. I mean, basically it's linear. It is linear. Yeah, so fine. Yes.
If there's a finite number of points where f double dash is 0,
Okay.
then we command the and the rest of the points, let's say it's negative 1.
Can you give an example of such a function?
X cube.
Okay, x cube.
For x greater than equal to 0.
X cube for x greater than or equal to 0.
The derivative is 0 at 0.
Okay.
Just 1 point.
Okay.
And let's say for all other points we know that it's convex. Did we still call the function?
Why do you say x cube is over what interval?
X greater than equal to 0.
X greater than or equal to 0. Okay.
It's convex.
It is convex. Yes.
For all x greater than
Correct.
0. But
At 0, so it's for all x greater than or equal to 0, it is convex. Because the second derivative is greater than or equal to 0 for all points in the interval. It's a smooth function, so you don't have the second derivative switching signs all of a sudden at finite set of points. Correct. So this is a function defined on R to the n, or in general it can be over any vector space. And this can be any norm, doesn't necessarily have to be the 2 norm. What can you say about this function? It's convex. Correct. So we just go back to the definition of convexity. So you take f of alpha x1 plus 1 minus alpha x2 for some alpha between 0 and 1, and any 2 points x1 and x2. This is equal to the norm of alpha x1 plus 1 minus alpha x2. But just by triangle inequality, we know that this is less than or equal to norm of alpha x1 plus norm of 1 minus alpha x2. Triangle inequality of norm, but then also using the property of norm, or the scaling property of the norm, that norm of alpha times x is alpha times the norm of x, or mod of alpha times the norm of x. Here alpha is greater than or equal to 0. So this is alpha times norm of x1 plus 1 minus alpha norm of x2, which is just alpha f of x1 plus 1 minus alpha f of x2. So this is convex for any norm. Again, the second derivative may or may not exist, right? So for example, if you take the 1 norm, right? So it's the sum of mod x. So let's take something even simpler. F of x is equal to mod of x. How do you prove that this is convex? Can you prove that using the second derivative test? You can't. Yeah, then you can potentially just correct. No, right? So what would be the second derivative test for functions on Rn? You have to look at the Hessian, right? That's why that would be more complicated. Even if you want to prove it for the 2 norm, you would have to compute the Hessian, and you have to show that the Hessian is positive semi-definite. This is a much easier approach. So for functions on R, the second derivative test is very easy. But for general functions on Rn, it's more difficult using the second order test. So here are some more example functions. Let's not do that right now in class, but I leave this as a homework. So you look at mod x to the power alpha for alpha, let's say greater than or equal to 0, x log x for again x defined over x in 0 to infinity, so suppose I have a vector, so f from Rn to R, f of x equal to max for all I in 1, 2, 3 up to n of xi. So basically it outputs the largest component in this vector. Log summation I equal to 1 to n e to the xi. The geometric mean. So using the various tests that we've seen so far, you can try to prove that each of these, in fact, all of these are convex functions. Okay. Now we'll see some functions or some sets correspond that can be defined using convex functions. Okay. And these will in general turn out to be useful properties for things that we want to show later on. So one we've already seen, but the first is the notion of a sublevel set. So for any function f, right, and any, say, alpha in R, we'll define the sublevel set or the alpha sublevel set as C alpha to be the set of all x in Rn such that f of x is less than or equal to alpha. Okay, so suppose I have the following function. Let's assume that I have a convex function defined on R. What would the sublevel set look like? Any sublevel set. Take any alpha. What would the sublevel set look like? It's again, so for it's a function defined on R. So the sublevel set will be some subset of R, right? So what would that look like? So this is x. This is a plot of f of x. So C alpha for any alpha is a subset of R. It's not parallel, it's a subset of this, right? So close it will be an interval, right? It will just be a closed interval. Right? So if you take any particular alpha, the sublevel set for this particular alpha is basically the set of all x for which f of x is less than or equal to alpha, which is this interval here, right? This is your C alpha. Okay. Now, if the function is not convex in general, so if it's some general set, then if I take, let's say, this particular alpha here, then the sublevel set could be a union of disjoint intervals. Okay, it's the union of this interval and this particular interval. But for a convex function, the sublevel set is always going to be an interval. I'm looking at functions on R. But more generally, if f is a convex function, then on any Rn, on any space, the sublevel set will always be a convex set.
Sir, can we say that product is convex because the sublevel is only one set?
So I'll come to that in just 1 minute, right? So right now the point that I'm making is that if f is convex, then all sublevel sets so C alpha for any alpha in R is convex. Okay, it's not just for one particular alpha, it has to hold for all alpha. So no matter what alpha I choose, the C alpha is always going to be a convex set. Now if I choose alpha too small, so if for example alpha is negative in this particular example, I just get the empty set and the empty set is convex. But can I claim the converse? Suppose I have a given function and all sublevel sets happen to be convex. Then can I claim that the function is convex? So this statement is fine, right? If f is convex, then all sublevel sets are convex. Yeah. So the function has to be well defined on an interval. It may or may not be continuous. That's a different story. But it has to be defined on all of Rn or whatever set that you're considering. Okay. So all of these statements are made only in the domain of f. Okay. So the question is, if for some function f, all sublevel sets f, so C alpha defined to be set of all x in Rn such that f of x is less than or equal to alpha. If this is convex for all alpha, then is f convex? Yeah. So I'm saying that it is convex for, so this set is convex for all alpha from minus infinity to plus infinity. But does it necessarily imply that f is also convex? How many think it is yes? How many say it's no? Okay, why in either case? Correct. Exactly. So if you take any monotone function, right, it need not even be convex. It need not be convex, concave, or anything of that sort. As long as it is monotone, the sublevel set is always going to be an interval, right? It's going to be a continuous interval. In this case, if it's monotone, then it's going to be an interval minus infinity to something, correct? But this function is not convex. Another example is you just take f of x to be equal to log x or x cube, anything. These functions are not convex, log x is concave, but all of the sublevel sets are convex because they're continuous intervals, right? So this is only a one-way condition. If the function is convex, then all sublevel sets are convex. If the function is not increasing, again, this is only over R, right? What about general Rn? It's still possible to have non-convex functions have convex sublevel sets. Let me see. Well, monotonicity, in general, I don't think so. You could come up with some weird examples where it's not monotone, not convex, but still the function, the sublevel sets are convex. Yeah, so if you think about something that looks like this, right? Right, this is not convex, but this function, all the sublevel sets are going to be convex. So in some sense, take a particular point on each. So to the right of this particular point, the function is monotone. To the left also, it is monotonically increasing, right? So in this interval, it's monotonically decreasing. In this interval, it's monotonically increasing. In fact, you can choose any function. You pick a particular point. To the right of that particular point, you take a monotonically increasing function, convex or concave. To the left, again, monotonically decreasing, but it need not be convex. But for the resulting function, all sublevel sets are going to be convex. Okay. So this statement requires a proof. Right? How do you prove something like this? Just use the definition of convexity, right? So again, I won't prove it here. I'll just leave that as an exercise. It's simple enough. I'm sorry? Correct. No, why does it imply that the sublevel set is convex? Correct. True, but for example, if f is not convex, then C alpha need not be convex, right? Right? It's not true for all functions. It's only true for convex functions. So you need to use the property of convexity somewhere, right? And the main idea is that, so to prove convexity, you take any 2 points in the sublevel set, x1, x2. You want to show that alpha times x1 plus 1 minus alpha times x2 also lies in the sublevel set, right? And that just follows because you take f of alpha x1 plus 1 minus alpha x2, you know that it is less than or equal to f of alpha times f of x1 plus 1 minus alpha times f of x2. But both f of x1 and f of x2 are less than or equal to alpha because they belong to the sublevel set. So, and that also belongs to the sublevel set. That's in R, but in general, we're making this claim for any subset of Rn. Right? So the function could be defined on Rn. So in the case of real functions over the reals, all convex sets just correspond to intervals, continuous intervals. But in Rn, it could be any complicated looking convex set. Okay. Another function, another set that again we've seen before is what I call the epigraph. So if I have a function from Rn to R, the epigraph of f is a set in Rn plus 1. So it is a set of all x comma t in Rn plus 1 such that f of x is less than or equal to t. So it looks similar to the sublevel set that I defined, except that the sublevel set was defined for a particular alpha, right? Set of all x for which f of x is less than or equal to alpha. Whereas this is a set in Rn plus 1. Right? So let's just take an example or two function on R. Take any function. What would the epigraph be? Like geometrically, how do you describe the epigraph from this definition? This is my x, this is my f of x. So this is a function defined over the reals, but the epigraph is a function in R to the n plus 1, or in this case R2. That would be the second order code, sure. But in general, like what is the geometric description of the epigraph? Exactly, the area above the curve, right? It's the entire region above the curve. Correct? So in this case, if we just write down this definition, the epigraph of f is simply the set of all x comma y such that f of x is less than or equal to y, or y is greater than or equal to f of x. So y equal to f of x just gives me this curve. Y greater than or equal to f of x gives me the entire region above the curve. So the epigraph is nothing but the entire region above the curve. Which one? So f of x is less than or equal to t, or t greater than or equal to f of x. So it would be this entire region, and this holds in general in Rn. If you think about a function defined on R2, right? So you think of a surface, you geometrically try to visualize any surface. The entire region above this surface is the epigraph. So now if F is convex, then what can you say about the epigraph? What kind of a set is the epigraph? Yeah, it's going to be a convex set. So if F is a convex function, then the epigraph of F is going to be a convex set. And in fact, the converse also holds in this particular case. If the epigraph of F is convex, then the function is convex. How would you show this? So suppose that F is convex. Yeah, so you take any 2 points. You want to show that the epigraph is convex. Right? So you take any 2 points. You take x1 comma t1 and x2 comma t2, which belong to the epigraph of F. You want to show that the convex, any convex combination of these 2 points also lies in the epigraph. Okay, so effectively I'm taking any 2 points within this set, right? Maybe this point and this point, and I want to show that the straight line joining these 2 points also lies in, basically lies above the curve. Okay, if in this particular example, which is not convex, where the function is not convex, I could potentially take this point and this point, in which where the straight line joining the points does not lie above the curve. Correct. So if you think about this, this is only a slight generalization of the definition of convexity, right? The definition of convexity basically said that you take any 2 points on the curve, the straight line joining these 2 points should also lie above the curve. Here, in this particular statement, all I am saying is you take any 2 points above the curve, not necessarily on the curve. You take any 2 points above the curve, the straight line joining those 2 points will also lie above the curve. Okay, so let's just use the definition of, let's first see if this belongs to epigraph of F. We want to show that alpha x1 plus 1 minus alpha x2 comma alpha t1 plus 1 minus alpha t2 so does this belong to epigraph of F? Simple thing, just evaluate this. So take f of alpha x1 plus 1 minus alpha x2. By definition of convexity, this is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. But we know that f of x1 is less than or equal to t1 and f of x2 is less than or equal to t2, because x1 t1 and x2 t2 both lie in the epigraph. this is less than or equal to so this therefore the set is convex. The epigraph is convex. So you can prove the other way around as well. If the epigraph is convex, then the function is also convex. In fact, if the epigraph is convex, you only need to consider points on the curve. You don't need to consider all possible points inside the curve.
This in some sense is everything above the sublevel set.
It's not exactly above the sublevel set. So you can think of it as, so you have whatever, let's look at alpha comma C alpha, so to speak, right? So for each alpha you have a sublevel set C alpha. Remember that the sublevel set is a subset of Rn, but the epigraph is a function, is a subset of Rn plus 1. So you take a alpha comma C alpha. So this, you can think of this as one sublevel set, but it's also coupled with the particular alpha which defines the sublevel set. So what is the epigraph in terms of these elements? Yeah, not really. So if you think of this as one sort of set, a single element, it's kind of the union of these, right? It is a set of all alpha comma x for which f of x is less than or equal to alpha. Right? So for a given alpha, a sublevel set is essentially an interval, right, over here. But again, intuitively, this is just, if you look at the set of all alpha comma this particular interval, this is you can think of this as this interval instead of this particular interval, right? And the union of all of these intervals would give you the epigraph. Sorry? Correct. So the epigraph is always the set of all points above the curve, right? So a slight modification of the definition of epigraph would give you, sorry, a slight modification in the definition of the sublevel set would give you the epigraph. That's what I'm trying to say. So the epigraph is always a subset of Rn, right? In this case of X, of R, right? So if I looked at the set of all alpha comma X so C alpha, the way it is defined, is the set of all X such that f of X is less than or equal to alpha, right? let me make a slight modification of this definition. Let me say that whatever C bar alpha is the set of all alpha comma x such that f of x is less than or equal to alpha. Okay, so for a given alpha, what would this set look like? So C alpha, let's fix a particular alpha. Let's say this is my alpha. Right? So C alpha would basically be this interval. This is my C alpha. Right? But what would this C bar alpha look like? Yeah, it would be this straight line, right? Again, it's set of all alpha comma x, set of all, so x comma y, if you want to think of it, right? So the one coordinate is fixed to alpha, the other coordinate is basically allowed to vary. So in this particular one-dimensional curve, for this one-dimensional curve, this is nothing but it's a shift of C alpha. You take C alpha, you shift it above by alpha. Correct? You take any other alpha, let me take alpha, some alpha 2, then C bar alpha 2 would basically be this set. This would be my C bar alpha 2. This is my C bar alpha 1. This is my alpha 1. And so on. So for each alpha, I get some kind of a horizontal line. Okay, except that this horizontal line is not a subset of the x-axis. It is shifted above. Okay, and the union of all of these C bar alphas, that would just give me the epigraph. Again, this is only in R. In general, sure, I mean, you could also consider the epigraph as a union of line segments. Take any 2 points on the surface, for example. It's again a union of uncountably infinitely many line segments. But you could also think of, in this sense, you could think of it also as a union of these sublevel sets, sort of shifted sublevel sets. Okay, but this notion of the epigraph has some other nice geometric interpretations as well. Because let's think about the first order test for convexity. Okay, this was a point that I brought to you some time back also, but in this particular context, it's helpful to recollect this. So you take the first order test for convexity. For convexity, that basically said that if you have a convex function, then the tangent at any point is going to lie strictly below the function. So take any convex function, take any point on the curve, the tangent at that particular point is going to lie below the curve. So that was the first order test for a convex function. Now let's think about this in terms of the epigraph, right? So the epigraph is now this particular set. The epigraph is this particular set. If I take any tangent on the curve, what does this correspond to for the set itself? Yeah, it's a supporting hyperplane, correct? And what have we seen for about the supporting hyperplane for convex sets? Exactly. So is an intersection of the supporting hyperplane, or in other words, there exists a supporting hyperplane at every point. So in other words, if I take a point and consider supporting hyperplane, the entire set lies on one side of this plane. Correct? So if I construct the supporting hyperplane, then the entire epigraph would lie on one side of this supporting hyperplane, or in one half space defined by this supporting hyperplane. Correct? And that the two notions are exactly the same, right, geometrically speaking, because one is saying that the tangent is always, so the curve is always above the tangent, which means that the epigraph is always going to lie above the tangent, so to speak. And that's the same as saying that if I consider the supporting hyperplane, then the entire epigraph is on one side of the supporting hyperplane. So many ideas or many geometric results for convex functions can be translated to convex sets and vice versa through this epigraph. Any questions? Okay, so let's again go back to our original definition of convex functions, right? So if f is convex, let's say f from Rn to R is convex, then we know that alpha f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. But I can also generalize this to more than 2 points. I can look at m points and take a convex combination of those m points. What would the convex combination look like? Correct. So summation alpha I xi, but the summation of all the coefficients should be equal to 1. Correct. So in general, f of summation I equal to 1 to m alpha I xi should be less than or equal to summation I equal to 1 to m alpha I f of xi. Alpha I greater than or equal to 0, and the summation of the alpha I should be equal to 1. Alright, but this has a particularly nice interpretation in probability. So you look at these alpha i's, all of these alpha i's are non-negative and they sum to 1. So what does that remind you of? It's a probability mass function, right? So you can think of the alpha i's as a probability mass function, in which case what is summation of I alpha I xi? It's just the expectation, right? And the right hand side, so this is you can think of a random variable x such that the probability that x equal to xi is equal to alpha I. Okay, so this is the probability that x is equal to xi. So here we are assuming that x can take one of m different values, x1, x2, x3 or xm, and you pick xi with probability alpha I. So in this case, expected value of x is equal to summation I equal to 1 to m alpha I xi. Correct? But what about the right hand side? What is that? That is also an expectation, but expectation of what? Okay, but what specific transformation? It says expectation of f of x. All right. So expectation of f of x is by definition summation I equal to 1 to m alpha I f of xi. Right. Each xi is a vector, but f of xi is a scalar random variable. So you can take yi to be equal to f of xi. So each xi is a vector, so f of x is going to be a scalar random variable. And the left hand side is f of expectation of x, whereas the right hand side is expectation f of x. So this basically says that for any convex function, f of expectation of x is always less than or equal to expectation of f of x. This is, in other words, just another interpretation of the definition of a convex function. But this has a special name, it's a special result called Jensen's inequality. And this interpretation is particularly important in information theory, statistics, and so on. It's widely used, and many results are derived just as byproducts of this particular inequality. Okay. In fact, just using these, you can prove results which are totally unrelated to even information theory. For example, let's suppose that I want to prove the AMGM inequality. Okay, what does the AMGM inequality say? Right? What is the geometric mean of two numbers? Yeah, it's root AB. Root AB, and what is the arithmetic mean? A plus B by 2. So if I take any two numbers, what can you say about the relationship between the arithmetic mean and the geometric? Yeah, the geometric mean is going to be less than or equal to the arithmetic mean. So this is the AMGM inequality. But let's say I wanted to prove this. Okay, how would I go about trying to prove this particular statement? Just using, let's say, Jensen's inequality. Exactly. So take log on both sides. So proving this is the same as proving that log root AB is less than or equal to log A plus B by 2. Right? But log root AB is just half log A plus half log B, less than or equal to log A plus B by 2. And I can get this directly just by applying Jensen's inequality. On what function? Yeah, so f is in fact the negative of the log, because log is concave minus log is convex. So you can prove a slightly more general version of the AMGM inequality, because this holds for the specific convex combination of half and half, but in fact a to the power alpha b to the power 1 minus alpha is going to be less than or equal to alpha times A plus 1 minus alpha times B. That's a slight generalization. But using this, you can also prove the Cauchy-Schwarz inequality, or more generally what is called Hölder's inequality. So given any two vectors, so this says that if I have any two vectors x and y in Rn, then the inner product xi yi is always going to be less than or equal to the p norm of x times the q norm of y. Xi to the power p so for any pq satisfying 1 by p plus 1 by q equal to 1. Again, I won't particularly prove this, but it's not very difficult to show this. Just using Jensen's inequality and maybe this particular version. Any questions? Okay, so maybe this is a good point to stop. In the next class, I'll introduce different operations that preserve convexity. We've already seen one, that linear combinations of, or conic combinations of convex functions give you convex functions. But we'll see that holds more generally. In fact, one other point I'd like to make over here regarding the Jensen's inequality is that in this case we took expectation of discrete random variables, but in fact this can be generalized continuous random variables as well. That's so this statement holds not just for discrete random variables, which was what we used to define convex combinations. So you can define a more generalized notion of a convex combination as integral of alpha times x, alpha of x times x, where alpha of x is a general function which is non-negative and whose integral is equal to 1. Okay. So in this case, we can apply Jensen's inequality as well. And in fact, many of the other statements that we'll make later on also hold under this generalized notion. So it's true not just for finite combinations of functions, but you can also look at infinitely many functions and combining infinitely many functions to produce one new convex function. Okay, so let's stop here.